Okay, welcome back everyone to our first full lesson. Now, this is of course going to be kind of an experiment in and of itself because I have not screencasted before for a lesson. So we'll see how well this works. We're going to try our best right now. So the first thing I'd like for you to do, please, is just we kind of review real quick where we left off. It seems like a lifetime ago. We were talking about the idea of waves. And remember, all a wave is basically some disturbance that carries energy from from one place to another. Okay. And we did throughout kind of the week and a half, 2 weeks, we did this. We talked about how waves move through things, how fast they can move. We talked about the idea of what happens when multiple waves run into each other. And our warm up today is actually kind of based off of that. So I would suggest hopefully getting out your notes. Hopefully you didn't just all throw them away as soon as you heard Friday that, school is closed for an extended period of time. And your warm up, if you could please, is I want you just to basically draw a couple wave pulses. And I want you to draw what happens before they run into each other, they interfere, when they interfere, and after they interfere. Okay. Now, I only have 15 minutes to do this video because they haven't paid for us to have the nice deluxe version. So I want you to take 2 minutes to do it. I'm not going to wait 2 minutes. So at this point, if you just want to pause the video, give yourself 2 minutes and then unpause it because in about 10 seconds, I'm going to reveal the answer. So if you could please take 2 minutes to do this warm up. All right, so let's see, ladies and gentlemen, what you have. So I drew these, just kind of sketched them. They're beautiful, hand-drawn originals by myself, and they look like it, of course. So when we draw these wave pulses, remember, all wave pulses do when they interfere with each other is they just kind of combine amplitudes. In this case, one is positive, one is negative. So originally, when they come towards each other, one has positive, one has negative. When they interfere, because the two of them, one is up and one is down, they actually are destructively interfering. So when they combine, they become much smaller for that split second. And then they just keep on going like nothing ever happened. Okay. And that's exactly what we're seeing right here in this little drawing to the right. So just kind of a little reminder of how waves work, because what we're going to talk about today is very dependent on how waves interfere with each other. Okay. So what we're going to talk about today is something that we call a standing wave. And most of you have actually already done this and you don't realize it when you were playing around with the springs when we were doing all of our labs. So let's look at this little simulator right here. So I have here a string. And just like we've done before, I'm going to just kind of throw a little wave pulse on it. And I'm going to change a couple things just so that it works. So basically, I'm just going to send a wave pulse. And as we saw before, the wave pulse is just going to bounce back and forth and back and forth and back and forth. Now, we talked about this idea as well that because the end is fixed, remember when it reflects, which is what we say when it just bounces back, it's upside down. Okay. And we're going to find out that actually is important to what we're going to talk about today. Now, I have one wave pulse in here, but in reality, usually you have more than just one little wave pulse going on. You have lots of waves traveling at once. So let's say I wait for this to get to the end and I throw another wave. Okay. We start to see kind of this more complex, weird action going on. And as we start to see is that when the waves run into each other, remember they interfere, they'll cancel each other out for a split second. And then I can just send a couple more in there. And of course, start to see, some really weird things are starting to happen. Okay. And I just start throwing more and more pulses. And basically what starts to happen is these really complex waves start to be made. And most of the time, they don't mean much to us because they look something like this and they look like garbage. But occasionally, if you go up and down at the right frequency, if you happen to go up and down just enough, what starts to happen is these waves almost look like they start to freeze in place. And what happens, flipping to our next screen, is that we create something that we call standing wave. Okay? And what that would look like, and it's going really slowly, so I'm going to speed it up just a little bit. What that looks like is basically a wave that looks like it's not going anywhere. It's just bouncing up and down. Now, in reality, what's happening, and most of you actually did this with your big slinky because you thought it was really fun until I told you you were going to break it. What is happening is that there are actually multiple wave pulses going on at the same time. but they're lined up just correctly, just enough that they actually kind of combine to make one wave that just look like it's going up and down and up and down. And it looks like that because it's standing there, as we call it. It's not moving. Okay. Now, what we're going to find out with standing waves is that they can look very different and they can produce very different sounds depending on what's going on. So this is like the most basic standing wave. It just looks like a big, like I just took a rubber band and just kind of twanged it and it started going up and down. Okay. Now I have the master notes, so feel free if you want to copy now exactly what I've written down for my descriptions. But basically, what we're going to say for a standing wave is it's just a very unique type of wave. It just looks like it's standing in place. And really what's happening is that all the waves in the string are just interfering with each other, and they're interfering in such a way that it just looks like in some places there isn't a wave at all. And in other places, it looks like the wave is bouncing up and down very quickly. And just to give us an example of something that is not as a bit more complicated, but still a standing wave. This is a really simple one. But I can, let's see, up it a little bit. And now what I've done, and we're going to explain what all this means because there's a bunch of new words on the screen. We're going to explain what it means in a second. What I've done is I've created a standing wave. Because what it looks like is it's basically just bouncing up and down and up and down and up and down. And what's happening is all the waves in there are interfering in such a way that it creates this pattern. And we're going to find out that actually the wave that's being made, whether it looks like this one, or I keep going, actually affects what you hear. Okay? Because we're going to tie it back to music a little bit today. So that's a standing wave. Now, we're going to draw real quick what these waves look like because there are a couple features that are really important for standing waves. So the standing wave, we just defined it. If you could, off to the right side, I'd love if you could sketch this real quick, the little thing that I have right here. This is just an example of kind of one version of a standing wave. And it's basically just like what you saw in the little simulation. It's a string that's stuck between two places, and it's just bouncing up and down. Now, with waves, specifically standing waves, there are two specific features that matter. One of them is referred to as a node. And what that means is that with a standing wave, you basically are looking for nodes and what we call antinodes. Now, the node is a very simple feature on a standing wave. It's the part of the wave where nothing's happening. So if we look at our simulation, everywhere where it looks like the wave is just kind of sitting there not doing anything. So in this case, it would be here, 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 and here is what we refer to as a node. It's a place where the amplitude is always zero, okay? And it doesn't matter how it's set up. In a standing wave, a node always has an amplitude of zero. Now, for an antinode, that's going to be where the amplitude is at its maximum. That's going to be the spot where it's bouncing up and down its highest amplitude. Okay, and in this case, that would probably be here, 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 just looking at every place where the wave looks like it's bouncing up and down at its maximum. Okay, those are what we refer to as antinodes. And one of the ways we're going to find is that nodes and antinodes are very important because they can define how the standing wave gets set up. Okay, and there are actually three different ways you can set up a standing wave. The first, and I apologize, I know this is very tiny, but the first is you have a standing wave set up where both ends are attached to something. Now, this can be, to give you kind of an example in real life, this would be the equivalent of any sort of stringed instrument. So a violin, a guitar, a cello, they're all something that has the string attached at both ends. And what happens, and we actually saw this little video with it, what we see is that as you make the string vibrate, if you can get it to vibrate at the exact frequency it needs to be, it starts to form this standing wave and it basically bounces there. Okay. Now, the most important thing with a standing wave is that the nodes, it always starts with a node and it ends with a node. Okay. And we're going to find out that for any of those where the ends are attached for that type of standing wave, that's going to be very important. Now, the second type of standing wave you can create is referred to as a standing wave where the ends are open. Now, this looks a little bit strange, and if we go back to our simulation, we can look at it with two opened ends. Okay? What it looks like is almost like I took, once again, part of the wave, and it just is oscillating back and forth based off of the little center point. Now, what's happening is that you're seeing half of a wave. And this is basically the least amount of wave I can get oscillating in this thing to create a sound. What we find with a standing wave with open ends is that it has a node in the middle and two antinodes on either side. Okay. Now, the best example I can give you are a lot of woodwind instruments are actually designed to create standing waves where they're open at both ends. The best example would be a flute. A flute is specifically designed so that you have both ends open, and you create different standing waves because of that. All right. Now, the third and final type we're going to talk about is a standing wave that only has one end that's open. Okay. Now, this would be the equivalent of pretty much the best example I've run into is a clarinet, where basically one side where your mouth is, where you're blowing into the clarinet, into the reed, that would be considered the closed end, whereas the end of the clarinet would be the open end. And what you get is kind of a more distinct, a bit stranger wave pattern, but it still creates a standing wave. And what would happen, just like this is for two open ends, it's bouncing back and forth. With one open end, it just looks like this. Now, one thing I do want to point out before we talk about the next step is the fact that when we talk about these standing waves, it only works for certain frequencies. I can't make a standing wave happen all the time. I can only make it work when I have it oscillating exactly right to get it to create these standing waves. Now, whenever you have two fixed ends like this, where you have a wave where the ends are open, what you actually find out is that this is half a wave. This is the lowest note, the lowest frequency that you can play in whatever musical instrument or whatever thing is creating the standing wave. And this is going to be half a wavelength, because a full wavelength is going to look like it starts here, then it goes up, then it goes down, then it comes back. This is only going to be half of that. And the same thing actually is true with two open ends, though it's not as easy to see. But what we actually find out is that this is also half a wavelength, and that this is producing a sound that's at a specific frequency that matches with something that has a full wavelength for this. And I do apologize. I know it's not super easy to explain via screencast. I'm going to post some other information as well, some other material. We'll try and go live. We'll see. But right now, this is just kind of the base stuff for what it looks like to create a standing wave. Okay, so I'm going to take a minute just to kind of let you write some stuff down, think about a little bit what you said. If you have questions, please feel free to email me. We're going to try and do this live at some point too. But right now, just take a second to think about and maybe draw these things. I'll be back in one sec.